Okay, so just to remind you, this is where we ended up last time. We were trying to understand how to take the infinite volume limit, because that's the only way you can get a phase transition anyway. And the first approach is the obvious one. You choose a sequence of boxes in your infinite graph, which I'm taking to be ZD. You take for each box a boundary condition. You choose some configuration of these spin variables sigma on the exterior of the box, but again, really all that means is on the external boundary of the box. You consider the model, you consider the Hamiltonian with those spins fixed on the boundary of the box. You consider the Gibbs measure in finite volume with those spins fixed. And then you take the weak limits of these Gibbs measures, and that's I should mention that because of compactness, it's guaranteed that there will exist some weak limits of subsequences. So there's no problem with Gibbs measures existing. The question is, might there exist more than one Gibbs measure for different choices of boundary conditions, or even conceivably different subsequences of boxes? And that's far from obvious. That's the kind of thing you have to study case by case in statistical mechanics. But in any case, any measure that you get as a weak limit of these things we define as an infinite volume Gibbs measure. And for each model, one wants to investigate what is the structure of the set of infinite volume Gibbs measures. And as I mentioned at the end of last time, the disadvantage of this approach is infinite volume Gibbs measures are defined by an existential condition, which is very difficult to check. You have to imagine all sequences of boxes and all boundary conditions. So here's an alternative approach due to De Bruch and Lansford and Ruel, which is equivalent to the elementary approach, but is much more convenient for checking. So the definition is, consider a probability measure mu on the infinite volume configuration space. So minus 1, 1 to the ZD. Such a probability measure is called an infinite volume Gibbs measure if, for all finite subsets lambda of ZD, the conditional probabilities for the spins inside, given the spins outside, are what they should be. That is to say, the conditional probabilities in the measure mu, which is the measure we're trying to test to see whether it is an infinite volume Gibbs measure, if those conditional probabilities are equal to the formula I gave you on the last slide for what the Boltzmann-Gibbs measure in volume lambda with boundary condition sigma d lambda is, if for every volume lambda those condition and every boundary condition sigma lambda complement, those conditional probabilities are what they should be, then this is an infinite volume Gibbs measure.
So this is reminiscent of the topology of convergence on compact sets.
I'm sorry, say this again?
This is reminiscent of the topology of convergence on compact sets, because you are checking your consistency only on compact sets.
We're checking the consistency on for cylinder sets, I guess a probabilist would call it. We consider all events depending on finitely many spins. We look for every lambda at every event inside lambda. So this is an infinite set of linear equations for the measure mu, which, if they're all satisfied, we call it an infinite volume Gibbs measure. And then there's the major theorem in the subject is mu is an infinite volume Gibbs measure in the De Bruch and Lansford-Ruel sense if and only if there exist lambda n's going up to ZD and boundary conditions such that you get mu as a weak limit of the kind that I described on the previous slide. Now, I should say I've cheated a little bit, and let me say how I cheated. On the previous slide, I assumed deterministic boundary conditions. That is to say, the boundary condition is a particular configuration. I could have been more general and allowed stochastic boundary conditions. I could have said the experimenter, in preparing the probability measure in volume lambda, first throws some coins to determine what is his boundary condition, and then Okay? So the truth is, this equivalence is true if you slightly generalize the previous slide to allow stochastic boundary conditions. If you allow deterministic boundary conditions, you're guaranteed to get all extremal Gibbs measures. I'm not sure whether you're guaranteed to get all Gibbs measures. The word extremal comes in this way. One of
You
the
really believe even extremal?
What?
I even do not believe that.
Yes, you get all. I'll answer that in a second.
Is
So,
it a
so,
clause?
so first, let me explain the word extremal. These are linear equations on the measures mu. So any convex combination of infinite volume Gibbs measures, it's a probability measure because it's a convex combination, and it solves those equations because those equations are linear. So the set of all infinite volume Gibbs measures is a convex set in space of probability measures. In any reasonable topology, it's a compact convex set. And then there's a beautiful theory of Sokal, which explains how any point in a compact convex set can be written as the barycenter of a probability measure living on the extremal points of that convex set. In fact, this convex set is a simplex, which means that the Sokal representation is unique. Given any infinite volume Gibbs measure, there's a unique way of decomposing it as a probabilistic superposition of extremal ones. And the extremal infinite volume Gibbs measures are what a physicist would call a pure phase. So for example, in our Ising model, Roman proved yesterday that plus boundary conditions gets you one at low enough temperature, plus boundary conditions gets you one infinite volume Gibbs measure with strictly positive magnetization, and minus boundary conditions gets you a different infinite volume Gibbs measure with strictly negative magnetization. The convex combinations of those two have the following interpretation. The experimenter flips a coin with some probability p of heads and 1 minus p of tails, looks at the coin and decides whether to prepare the sample of iron with plus boundary conditions or minus boundary conditions. Having done that, he throws away the coin and hands you the sample of iron. Then what you have is a convex combination of the pure phases. So it's clear that it's the extremal Gibbs measures that are physically interesting. The non-extremal ones are just trivial probabilistic superpositions of the extremal ones. So it's really the extremal ones that matter. Now there's a very beautiful theorem that says the following. Take any extremal infinite volume Gibbs measure and take almost any configuration in that measure, use that configuration as a boundary condition, and take the infinite volume limit, you will get back the extremal Gibbs measure that you started with. So in fact, not only does every extremal Gibbs measure come from a construction of the previous slide with deterministic boundary conditions, almost any in the sense of with probability 1, typical configuration of that extremal Gibbs measure is self-reproducing. For example, if you have plus boundary conditions, typical configurations in that infinite volume Gibbs measure have most of the spins up and a minority of the spins down. Using such a configuration as a boundary condition is enough to get you back the plus boundary condition state. So there's a very beautiful theory, as I say, in either the Preston lecture notes in mathematics or in George's book that proves all this. And it's a probabilistic theory. It uses, for example, the proof of this uses the backward martingale convergence theorem.
This theorem is true at any temperature.
This is a total abstract nonsense.
No,
this is true in total abstraction for virtually any statistical mechanical model with virtually any Hamiltonian.
Your boundary conditions are random somehow.
I'm sorry?
Your boundary conditions are deterministic or random?
Or no, what I said was, the theorem I quoted had to do with deterministic boundary conditions. So I consider, let mu.
Because, there was a paper by Schur.
So let me state the theorem. Let mu be an extremal infinite volume Gibbs measure for a particular Hamiltonian. Okay? Consider the set A of configurations omega that have the property that if I use omega as a boundary condition, so fix a sequence of boxes lambda n. Let me now use omega as a boundary condition and ask, as I increase the volume, do these finite volume Gibbs measures with boundary condition omega converge? And if so, what do they converge to? Okay? And I will let A be the set of omegas that have the property that if you use omega as a boundary condition, these guys do converge and converge to mu. Okay? So let's call that the set of boundary conditions that reproduce mu. Then the theorem states mu of A is 1. Mu almost every configuration, when used as a boundary condition, reproduces mu.
So when this was proven?
73 maybe? Early 70s.
There is a paper by Shelley Goldstein from 80 or something like that, where he is saying, let us take an extremal Gibbs state such that it has this property, that it can be constructed as a limit. So this was somehow complicated assumption of his theorem. Whenever we have an extremal Gibbs state such that it can be constructed by the deterministic boundary condition, then something is right.
And maybe we should talk about it later because this is actually a side point. I mean, I just wanted to get across the point that there is this beautiful theory, and you don't really need to know the proofs of this beautiful theory, but the proofs are actually fairly simple. They're probabilistic. They're nice. It's a nice theory. But so the point is the Gibbs measures form a convex set. The extremal points in this convex set can be interpreted as the physical pure phases. Okay. Can I now get rid of the... hello? Go up, up. Thank you. So now I'll use the blackboard for a second because I want to interpolate here a discussion which Rollman assigned to me. We're assigning things to each other. So the question is, which quantities have good infinite volume limits? And one of them we saw with reasonable choices of boundary conditions, the Gibbs measures should have a good infinite volume limit. But we also had these partition functions, z lambda. Now, granted, they aren't so interesting because they're just the normalization factors. But as Roman already showed you, if you consider this as a function of various parameters and differentiate with respect to those parameters, then you get expectation values of things. So it is useful to ask what happens with the partition functions in the infinite volume limit. And the correct statement, as Roman anticipated, is these guys, the partition functions don't converge. What converges is 1 over volume log of the partition function. So log of the partition function is what we call a free energy. Well, Roman had, I think, a -1 over beta, but I will take the convention that beta equals 1 and -1 equals 1. So this is a free energy, and this is a free energy per unit volume. So you expect that the free energy per unit volume in the infinite volume limit has a good limit. Limit lambda goes up to ZD. And as Roman also anticipated here, there's a slight subtlety. When you look at the Gibbs measure, you take lambda up to ZD, and you can take any increasing sequence of sets whose union is ZD. Here, for the free energy, you should take a sequence of sets that are not too bad. And not too bad means their surface to volume ratio should go to 0. You should not take, what would be a good example? I guess if you were to take a sequence of n by n squared. No, Oh, no, that would be okay. No, well, you
Well,
shouldn't.
strip with infinite length.
No, just
and
take
zero
n times
infinite
logarithm
width.
n.
Says again?
N times logarithm n, for example.
And
Time log.
No,
we
because
can
you
add-
wanted to expand those, but if you take a small square of, say, side n, and then add a long thin tail of, say, n squared sides,
Right.
axis.
Anyway, you can think of parable shaped sets where the surface to volume, Swiss cheese type sets also, right? Where the surface to volume ratio doesn't go to 0. So here I want limit, this is the so-called Van Hove limit. So the limit where surface to volume should go to 0. So most reasonable sequences of sets will satisfy that. And then this limit should exist. And let me sketch for you why it's true. I won't prove it, but I'll show you the essence of the proof. Okay. So the first point is, I already defined the Ising model for an arbitrary graph. So let me look at a trivial case. Imagine that the graph is a disjoint union of two pieces, G1 and G2. Then it's obvious that ZG is the product ZG1, ZG2. Right? I mean, the two sums don't talk to each other. Now, of course, we're not in such a trivial situation. We're in a situation like this. Let's consider a very big piece of our, let's say, square lattice, and let's divide it into 4 big but smaller pieces of the square lattice. Okay? And let me call these G1, G2, G3, G4, and this whole thing G. Okay? Now, it's not true that ZG is the product of ZG1, ZG2, ZG3, and ZG4, because this is not a disjoint union. These pieces interact on their boundaries, right? But it's kind of close to a disjoint union because these surfaces are small compared to the volumes of the pieces. So more precisely, you can show that log of ZG over ZG1, ZG2, ZG3, ZG4 is bounded above and below by some constant, let's say that this is an L by L box, or L to the D in D dimensions. You can show that this is bounded by a constant times L to the D minus 1, the surface area. Okay, because basically the energy coming, but the point is the Hamiltonian in volume G is the Hamiltonian in volume G1 plus the Hamiltonian in volume G2 plus the Hamiltonian in volume G3 plus the Hamiltonian in volume G4 plus this extra term coming from the edges that cross the boundary, but there are only order L to the D minus 1 of such edges. So this here is order L to the D minus 1. So therefore, it's quite easy to prove this bound. So this says that log ZG is not quite additive, but it's almost additive. On disjoint subsets that abut each other, log ZG is almost but not quite additive. That's enough to prove that a limit like this exists. And the proof takes about 2 pages. It's not very difficult. You can find it, for example, in Robert Israel's book called Convexity and the Theory of Lattice Gases. In fact, you can find it in all of these books. And it's much more general. I showed it to you for the nearest neighbor Ising model, but again, it doesn't have to be nearest neighbor. It could be 17th nearest neighbor. It could be an infinite range interaction, provided that it's absolutely summable. It's provided that the absolute value of the interaction is the convergent sum. And it doesn't have to be 2 spin interactions. It could have 17 spin interactions. It could have anything. So in a huge Banach space of interactions, this is true. Yeah?
I mean, this particular proof works?
This particular proof works. If instead of nearest neighbor interactions you have range R interactions, then you just make corridors of width R. And if you have infinite range interactions, you make corridors of width R and you figure out how much is in the corridor and how much is out of the corridor and bound everything. So it just works in great generality. And moreover, so not only does it exist, it's also independent of boundary conditions, because the boundary conditions, again, only affect what's going on here. That's a surface effect. They will, again, if you compare two different boundary conditions, again, the logs of the partition functions will differ only by a surface area. And you take the infinite volume limit, you take the logarithm, and then you divide by the volume, and that disappears. Okay? So you see why you need boxes whose surface to volume ratio goes to 0. But if you consider those, the infinite volume limit of the free energy per unit volume exists and is independent of boundary conditions. Totally unlike the Gibbs measure, where the Gibbs measure depends on the boundary conditions. That's what phase transitions are about. Okay, now let's go back to the projector. Hello? Thank you. Okay, now I want to re-ask from a slightly different mathematical point of view. Where is the eraser? Oh, here. From a slightly different point of view, I'd like to re-ask the question of how do we get a phase transition? You saw that in finite volume there are no phase transitions. In finite volume everything is analytic, but what happens is, let's again look at the magnetization as a function of external magnetic field for our Ising model. This is the infinite volume limit. So what happens in finite volume, in some small volume you get a curve like that. In a bigger volume you get a sharper curve. And in the infinite volume limit it approaches this discontinuous function. And of course that's, from a mathematical point of view, what we see here is if Fn of x, think, for example, think of n as the volume, and Fn of x, let's say the magnetization as a function of external field. If Fn of x are analytic functions of a real variable x, and Fn of x converges to f of x pointwise, then the limiting function need not be analytic, it need not even be continuous. Right? You learn that in your first analysis course, and the prototypical example is Fn of x is hyperbolic tangent nx, which converge as n goes to infinity to a step function. In fact, it looks quite a lot like the Ising model. Okay, no problem. That's a well-known fact about real analysis. But take a look at this contrasting fact about complex analysis. If Fn of z are analytic functions of a complex variable z in some domain D of the complex plane, and Fn of z approaches f of z pointwise, then under very mild conditions, the limiting function is guaranteed to be analytic. For example, Vitali's theorem says that if the functions Fn of x are uniformly bounded on compact subsets of D, that's enough to get analyticity. In fact, there's a beautiful theorem of Montel that says if there are, I think it's if there are two values in the complex plane which are omitted by all of the Fn's, that by itself is enough to get the limiting function analytic. Incredible theorem. But in any case, so you see, under very mild conditions, a pointwise limit of complex analytic functions of a complex variable is analytic. What goes wrong with real analytic functions of a real variable? At first you think it's strange, because what is an analytic function of a real variable? Consider a little interval, this orange interval of the real axis. An analytic function of a real variable on that interval is nothing other than the restriction to that interval of an analytic function of a complex variable in some complex neighborhood. of that interval. So what goes wrong? How are these real analysis and complex analysis facts compatible? And the answer, if you think for a second, is each Fn, we fix some interval, some orange interval of the real axis. Each Fn extends to an analytic function in some domain Dn containing that interval. But the Dn's need not be uniform in n. That's the problem. Another way of saying it is the Fn's can have singularities in the complex plane off that real interval, which, however, get closer and closer to that real interval as n goes to infinity. They can pinch the real axis in the limit n goes to infinity, and then the limiting function could fail to be analytic. And think again of hyperbolic tangent of nx. If you can understand a lot about real analysis by thinking in the complex plane, right? Hyperbolic tangent of nx seems to be a nice smooth function. But if you think in the complex plane, it has, of course, on the imaginary axis, it's tangent. So it has poles at x equals plus or minus pi over 2ni, plus or minus 3 pi over 2ni, and so on. So it has poles on the imaginary axis which are approaching the origin as n goes to infinity. Pinch the origin in the limit, that's where the step function singularity comes from. Okay? So the point is that singularity, if you think complex, you can understand where a phase transition comes from. Singularities can come in from the complex plane and pinch the real axis in the infinite volume limit. Okay? Now, I have a slide on which I just talked about. The question is, what is the quantity that plays the role of the Fn? It's not the partition function. As I explained here, it's 1 over volume log of the partition function. Okay? Now, the partition function is an entire analytic function in the complex plane. As we saw, the partition function in finite volume is a finite sum of things of the form e to the aj plus bh. Right? Finite sum of exponentials. It's as analytic as it can possibly be. How can log of an analytic function fail to be analytic? There's only one way. What is it? The function can vanish. Right? So the only places in the complex plane where the free energy, log z lambda, can fail to be analytic are the zeros of the free energy. Those can't be on the real axis, because on the real axis, z lambda is a sum of positive terms. It's a sum of unnormalized probabilities. But off the real axis, you can get phase cancellations, and z lambda can be 0, and maybe those zeros of the partition function can approach the real axis as the volume goes to infinity, and this is the Yang-Lee 1952 picture of phase transitions and approach to studying phase transitions. It's one way, not the only way, but one way to study phase transitions. You take one or more physical parameters, such as temperature or magnetic field, which are physically real, and promote them to complex variables. I mean, this is kind of weird, right? I mean, you don't go to your experimentalist friend and say, please measure for me the specific heat of iron at 273 plus 6i degrees Kelvin. But nevertheless, from a mathematical point of view, you can promote these things to complex variables. So study the partition function as a function of the complex variable, j or h or whatever. Look for the zeros of the finite volume partition function in the complex plane, and ask where can those zeros accumulate in the infinite volume limit. Any real limit points of such zeros are possible points of physical phase transitions. And so that's, so maybe I should go off on the side for a second. So what I just told you now comes from a paper of Yang and Lee in Physical Review 1952. Okay? Back to back with that paper, there's another paper of Li and Yang, also, right? I don't know why, I mean, maybe, Robert.
No comment.
I don't know why, whether they were already fighting for priority way back then. I mean, they, a few years later, got the Nobel Prize for totally different work. So the first paper gives this general picture that I've just discussed, says, go complexify one or more of the parameters and look for zeros of the partition function. The second paper applies it by proving an incredibly beautiful theorem for the ferromagnetic Ising model. And let me just state this theorem so that you can see how beautiful it is. Maybe tomorrow I'll prove it. So here's the theorem. You consider a ferromagnetic Ising model, so arbitrary finite graph. In fact, I will just let the graph be the complete graph on n vertices. So I just have n Ising spins, sigma 1 through sigma n. And the Hamiltonian is completely arbitrary two-body interactions. So I just have arbitrary interactions, j, I, j. So arbitrary couplings on the edges of the complete graph. And then magnetic fields, also arbitrary and independent on the individual sites.
Alan, you want it to be ferromagnetic.
I'm going to get there. Okay, that's the Hamiltonian. And here are the conditions. The couplings are going to be ferromagnetic. Jij is supposed to be non-negative for all pairs ij. But otherwise, there are absolutely no conditions. Okay? And it's the magnetic fields, HI, that I'm going to make complex. Okay? So in applying this Yang-Li picture, you always have the decision, which variable do you make complex? So in this case, it's the magnetic fields we make complex, and the couplings are ferromagnetic but otherwise arbitrary. And here's the claim. If real part of HI is positive, strictly positive for all I, so if all of the complex magnetic fields have strictly positive real part, or by symmetry, if they all have strictly negative real part, then the partition function is not zero. So there's an enormous chunk of multidimensional complex space, namely the product of right half planes, where the partition function is guaranteed to be non-vanishing, and you know nothing about these interactions Jij except that they're ferromagnetic. Okay? And of course, corollary, if you set all the HI's equal to the same number H, that's what we do when we do experiments. We put the same magnetic field on the whole sample of iron. Then all zeros of Z of H lie on the imaginary axis. Because they can't lie in the left half plane. By symmetry, they can't lie in the right half plane. Therefore, they have to live on the imaginary axis. Which is amazing, because a priori you think they could lie anywhere in the complex plane. But no, they're stuck on a very specific one-dimensional curve. So maybe I'll prove this. Oh, and another corollary of this is phase transitions in a ferromagnetic Ising model occur only at zero magnetic field. Because everywhere else you have analyticity. Everywhere else on the real axis, you're part of the left half plane or part of the right half plane and have analyticity. And physically that makes sense, because I explained to you, as long as the magnetic field is strictly positive or strictly negative, there's no instability. All of the spins tend to follow the field. The instability where they want to get together with each other but don't know which way to go, that's only at zero field. But this gives a very strong proof of it. But what I want to stress for combinatorialists is not the physical corollary, but the original theorem is a multivariate theorem, proving a huge chunk of multidimensional complex space is zero free. And there are by now 5 or 6 different proofs of this theorem, and they all prove the multidimensional theorem. I do not know any way to prove the corollary without proving the more general multivariate theorem. Yeah.
Our paper.
Oh, you have it?
Sure.
Okay. Okay, I know of 1/7 of the existing proofs prove the corollary without the. Anyway, maybe on Thursday I will show you one of those 6 proofs of the Li-Yang theory. In fact, I think I'll simultaneously show you a proof of the Heilman-Lieb theorem on zeros of matching polynomials, which you may have heard of. Again, you've probably heard of the univariate version, but actually that's just a corollary of the much more powerful multivariate version. And I'll...
So that's your pick with Lieb that you're going to be talking about?
No. So Elliot Lieb and I had a paper 25 years ago about giving one of those 6 proofs we gave in 1981. I won't talk about that. I'll give you an even simpler proof that is in a paper with Dave Wagner and James Oxley and Youngbin Cho a few years ago. Okay. Let me switch gears a little bit. So I'll come back to these combinatorial things a little bit later. I just want to switch gears a little bit to show a third aspect of phase transitions, which may be of interest to some of you. It's of a lot of interest to computer scientists these days, and it has to do with torpid mixing of local stochastic dynamics. Let me maybe give a little bit of the motivation first. So we're interested in studying these Ising models and other statistical mechanical models. Most of them are not exactly soluble by analytic methods, so we have to do some kind of approximations. One kind of approximation is Monte Carlo simulations on the computer, which means you find some way or other of generating random samples from the Boltzmann-Gibbs measure, admittedly for a finite Ising model, but hopefully a sequence of larger and larger ones. And then you analyze that data. And so how do you generate random samples from the Boltzmann-Gibbs measure? The usual way, in fact the most efficient way that anybody's found out, is you invent a Markov chain that is of a stochastic dynamics, a way of taking an Ising configuration and updating it by some random process to give another Ising configuration. You find a Markov chain that has the desired Boltzmann-Gibbs measure as its unique equilibrium measure. And then you run this thing, start it in any configuration and run it, and it will approach equilibrium, and then you take data for a year or 10 years or however long you can use in computer time and analyze that data. So there are various kinds of stochastic dynamics that people use. And here's the simplest one. It's a local stochastic dynamics. This is called the discrete time single spin heat bath or Glauber dynamics. It's very, very simple. Choose one of the spins in your finite box, because we're simulating a finite Ising model. Choose one of the vertices I uniformly at random. Erase the current value of sigma I and replace it by a new value, sigma prime I, independent of the old value, chosen from the correct conditional distribution. Namely, you look at the neighbors, sigma j, a nearest neighbor of I, and you count how many of them are up and how many of them are down, and then you do a simple calculation with the Hamiltonian to figure out, conditional on those, what is the probability that sigma I should be up or down, and you choose a new sigma prime I with that probability. And then you just keep going. It's about the simplest dynamics you can imagine. It's very easy to prove that this Markov chain does indeed have the Boltzmann-Gibbs distribution as its unique invariant distribution, so that you start in any configuration and let it run for long enough, you will converge to the Boltzmann-Gibbs distribution. Of course, the problem is, how long is long enough? And so that's why the problem of rate of convergence to equilibrium for Markov chains is a big area of research in probability and theoretical computer science. It's of practical importance if you do Monte Carlo simulations of these models. So let me discuss one of the cases where it's clear that this algorithm works badly. That is to say, it works in principle, but it's extremely inefficient. It takes a long time to give samples from the equilibrium distribution. Consider low temperature, zero magnetic field. In infinite volume, as Roman proved, the Gibbs measure is non-unique. There's a plus magnetized phase and a minus magnetized phase. What's the story in large finite volume with, let's say, free boundary conditions? So large finite volume with boundary conditions that do not favor plus or minus, either free boundary conditions or periodic boundary conditions, some neutral boundary conditions. Well, there's a unique Gibbs measure. It's written down by the formula, but it has the property that it's strongly bimodal. That is to say, nearly every configuration in this probability measure will either look a lot like the infinite volume plus phase, namely have a sea of pluses with small numbers of dissident minuses in them, or it will look a lot like the infinite volume minus phase. There are very few configurations that look any different from those. And how do you know that? Well, what's the next most likely configuration after configurations that are typical of the plus phase and configurations that are typical of the minus phase? The next least unlikely thing is to take half the box separated by an interface and put typical of the plus phase here, that is to say mostly pluses with some small islands of minuses, and put typical of the minus phase here. But already, if you do that, what do you pay? You pay an energy price on this surface proportional to the surface area. So configurations like that are likely to be suppressed like exponential of minus some constant L to the d minus 1, where this constant is some kind of a surface tension. And so such configurations are extremely rare. On the other hand, what does our local dynamics have to do? It's supposed to explore this Boltzmann-Gibbs distribution, and the Boltzmann-Gibbs distribution has probability almost a half on configurations that look like the plus phase, and almost a half on configurations that look like the minus phase. And if it's going to explore this in any reasonable way, it has to go between these. But to go between these are local updates. How is the magnetization going to get from plus m0 to minus m0? You're flipping individual spins. The magnetization has to go through 0. And the least improbable way of going through 0 is this. Anything else is even worse. And so you're in a situation where you have to get from one highly probable set to another highly probable set. It's like, there are two towns where you want to live half the time, and there's this enormous mountain in between. And it's going to take you a time exponential to the plus CL to the d minus 1 to get over this barrier. And so you expect torpid mixing of the single site heat bath dynamics with an autocorrelation time that is exponentially large in the surface area. So that's an example of a simple case where you expect extremely slow mixing of a stochastic dynamics. And in fact, so you would expect torpid mixing of local dynamics whenever you're sitting on a first order phase transition. That's the moral. One thing I just have written in little tiny letters at the end, you expect critical slowing down at a critical point. What if you're not near a first order transition, but near a second order transition? So not Ising model at very low temperature and zero magnetic field, but Ising model and the critical temperature and zero magnetic field. Okay? Then things are not quite so bad. Instead of getting exponential slowing down, you get power law slowing down. L to some power. So-called critical slowing down. And again, it's a big part of non-rigorous statistical physics to try to understand what those dynamic critical exponents are. And it's a big part of rigorous mathematical statistical mechanics to try to prove upper or lower bounds on them. So I don't want to say more about that right now, but I just wanted to let you know, so just to remind you where I came from, that there were these three aspects of phase transitions that I've shown are somehow related, even though I haven't proved specific theorems relating them, and some of the theorems that we want may not exist yet. But you see that the concept of phase transition somehow includes three heuristically related things: non-uniqueness of the infinite volume Gibbs measure, complex zeros of the finite volume partition function converging to the real axis, and torpid mixing of local stochastic dynamics. Okay. Why don't I start now? But I'd like to start, so now why don't we go up again? Good. So what I'd like to do now is start on the next topic, which I think is very nice combinatorially. It was already mentioned by Dave Wagner in his talk. He mentioned the Fortuyn-Castellane representation. I'm sorry, are there any Dutch people here? Could you please pronounce for me those two names properly?
Fortuyn-Castellane.
Do it again?
Fortuyn-Castellane.
Okay, I'm sorry that when I visited Leiden, they spent about an hour trying to teach me to say Fortuyn? Fortuyn. Okay. Anyway, I'm sorry I can't pronounce his name properly. But these two guys, FK, proved a beautiful representation for the Q-state Potts model, which is of huge combinatorial importance. So let me try to discuss that in detail and actually prove the representation, because I guess, Dave, you didn't prove it, right? So
it was Bill.
I'm sorry?
It was Bill.
Oh, it was Bill, was it? Oh, I'm sorry, you're right, it was Bill. Where's Bill?
He's there.
Yeah, okay. Sorry, Bill. Okay, I'm totally, you didn't prove it either.
No.
Okay.
But I can't be blamed for that.
You can't be blamed for the fact that Bill didn't prove it.
Yeah, it's all right you said he did it. It wasn't so nice that he didn't prove it.
Okay. Well, he didn't prove it. Okay.
Why did he did?
Okay, so I have to first start by defining the Q-state Potts model. So Q is a positive integer. Q equals 1 is a little trivial, so let's say Q equals 2, 3, 4, so on. The Potts model is a generalization of the Ising model. So the Ising model, you have two states. I call them sigma equals +1 and sigma equals -1, but it doesn't really matter. There are two states, and nearest neighbors in the ferromagnetic case like to be in the same state and pay an energy price if they're in different states. The Q-state Potts model is exactly the same story. There are Q states, nearest neighbors in the ferromagnetic case like to be in the same state, pay an energy price if they're in different states. And the only thing that one cares about is same or different. Okay, one doesn't care. The energy for state 1 adjacent to state 2 is the same as the energy for state 3 adjacent to state 17, and so on. So the Hamiltonian, so I consider a finite graph again. And on the finite graph, and I have spin sigma I in the set 1 through Q for each vertex I. And so the Hamiltonian is minus sum on edges ij. I mean, the graph doesn't have to be simple, but it might as well be simple. So loops and multiple edges are trivial. So let me just write it as if it were simple. And then there is a coupling jij or je, if you call this edge e, delta of sigma I sigma j. So this is the Kronecker delta. It's 1 if sigma I equals sigma j, and 0 if not equal. That's the Potts Hamiltonian, right, H Potts. So then Z Potts is sum over all configurations. So basically all Q colorings, proper or not, of the vertices. So this is what Bill wrote down, right? Maps from V to 1 through Q, exponential of minus H Potts of sigma. I'm putting beta equals 1. Okay? I want to do some funny algebra with this. Where did I put the eraser? And derive a nice representation. Sorry. First thing I'm going to do is I'm going to say exponential of a sum is product of the exponentials. Okay? So I will write this, and then I'll write it in the following way. The point is, on each edge, there are two values for the energy, 0 or minus j. Therefore, on each edge, there are two possible values for the Boltzmann weight, exponential of 0 or exponential of j. And I'll write that additively. That is to say, I'll write sum over colorings, proper or not, product over all edges ij. And now I'm going to get the formula that Bill wrote. Or maybe it was Bill impersonating Dave. 1 plus, he called it WE, I'll call it VE. I know Bill doesn't like that because V should be reserved for vertices. But somehow in physics, one usually uses V. VE delta sigma I sigma j, where VE is e to the je minus 1. Okay? So that's another way, in fact, combinatorially simpler way, because there are no exponentials, way of writing the Potts model partition function. Okay? Now, I'm going to do the following thing. I'm going to expand out this product over the edges, and I'm going to use the following deep identity. If A and B are any two real or complex numbers, A plus B is summed from n equals 0 to 1, A delta n0 plus B delta n1, where deltas are the Kronecker deltas, right? Do you agree that this is an identity? I guess it's valid in any abelian semigroup. Anyway, I'm going to apply this identity, which means that on each edge, I'm going to introduce variable ne, which takes the values 0 or 1. Of course, what I'm really doing is I'm expanding out this product. And I'm just keeping track. For every edge, I have to either take the term 1 or take the term v delta. And I'm just keeping track of which do I take where. So let's say n equals 1 corresponds to taking v delta. So what do I get? In fact, I don't really have to use these n's. What I will just use is I will let A be the subset of edges where I choose v delta, which is the same as the subset of edges which have n equals 1. So I have to sum over all subsets A and E. That's equivalent to summing over all terms in this expansion. And then what do I get? Well, for every edge in A, I obviously get a factor VE. Then I also get delta functions that says for every edge, should I draw a picture? Here's my graph. G, let's say, and here is some particular subset A. Okay? And then so for a given A, then I have to sum over configuration sigma, over coloring sigma, consistent with the constraints that any two vertices connected by an edge in A must have the same color. So it's obvious what these constraints are. The subgraph VA divides up into connected components. In each connected component, the color has to be the same. You have Q choices for what that color is, independently for each component. And notice, including isolated vertices, those are also components. So for each connected component of the subgraph VA, you have Q choices. They're all independent. So you get Q to the K of A, where K of A is the number of connected components in the graph VA. So what have I shown? I've shown that the Q-state Potts model, which initially is defined for positive integer Q separately for each Q. There's no obvious relation between the 3-state Potts model and the 17-state Potts model. Nevertheless, the Potts model partition function is the restriction to integers Q of a polynomial in Q, in fact, a polynomial in Q and all of the VEs. And this polynomial is what we now call the multivariate Tutt polynomial. I write V vector for the collection of these edge weights VE, and we have this polynomial, which is a polynomial in the one global variable Q, which is the number of colors, and in all the edge weights VE, and it's manifestly a polynomial. You don't need deletion contraction to prove this. You have an explicit formula. Yeah, Gordon.
Well, in this case here, when your example, why don't you choose the same color for two different components that are connected?
Say this again? Oh, these were not supposed to be colorings. I just used red to mean the...
But if you did choose red for the 3 vertex bit and red for the other one, then you're...
No, that's legal. The edges,
Yeah.
remember how this goes. It's not have a coloring and then throw all the edges between neighboring vertices of identical color. No, that's not what it is. It's you throw edges, and then within any two vertices that are connected by an occupied edge must be colored the same. But still, distinct clusters that are adjacent can also be colored the same, right? So it is indeed each connected component has one color, there are Q choices, and each connected component is completely independent. These guys could be same or different. They're exactly Q cubed legal colorings for that particular A.
Is there another
Can you
question?
write the polynomial as a sum over the spanning trees?
Yes, this is, well, I don't know. It's not what Tutt did, but he could have done it, yes. There's an internal-external activity expansion for the multivariate Tutt polynomial, completely analogous to the one for the original Tutt polynomial. I don't know whether it's good for anything. I mean, as usual, good ideas are discovered mixed with irrelevancies. And Tutt discovered that his original two-variable Tutt polynomial initially through this incredibly complicated, to my mind, internal-external activity expansion, where you assume an arbitrary ordering of the edges, you define a polynomial that involves the arbitrary ordering, and then you prove that it's independent of the choice of the ordering, and I find that weird. I prefer to start with this explicit definition, and then, if you want, prove as a theorem it has an internal-external activity expansion. It does. The answer is it does.
Yeah, but the spanning trees is stable because you are summing positive terms, and here you have huge cancellations. So you can, if you want to do some estimation on what's going on,
I'm sorry, what do you mean by that?
if you sum over the spanning tree the usual Tutt polynomial, then you are summing positive terms.
Well, no, there are weights. I mean, you have x to the something, y to the something, and,
Yeah, that's
and
the
depending on what values you give to x and y, they might be positive, negative, complex, whatever. Right? I mean, we haven't, so at this point, this is totally algebraic. I didn't tell you, is V positive, real, negative, real, complex? Is V just an algebraic indeterminate? At this point, it doesn't matter. Later, next week, we're going to make things analytic, and I will make V and Q complex, Bill will make V and Q real, and so on. But at this point, this is just an algebraic identity. Okay, I should stop now. So next time I'm going to continue a little bit with the multivariate cut polynomial, and then I think I'll give you a proof of the Li-Yang and Heilman-Lieb theorems because it's so beautiful. Okay.